So in this talk I will present my contribution to a class of star cluster formation models in which the volume density of the star-forming gas is the key parameter. But first let me give you a little bit of background. Why are we in the star cluster community? Why are we so much interested in the formation conditions of star clusters? After all, star clusters represent only a small fraction of the stellar content of galaxies. Nevertheless, they represent key tracers of the evolution of their host galaxies. And the reason is that, thanks to their mass combined to their compactness, they can be identified on a one-by-one basis against the background of their host galaxy. And once identified, their cluster, the cluster integrated photometry, can be translated into cluster age and cluster mass estimates. And you will note that I have underlined the word estimates. Once you have the cluster ages, for instance, you can build the cluster age distribution, which in itself is already very interesting because we know that star clusters form abundantly in galaxy mergers and galaxy interactions, and therefore if you observe a peak in the cluster age distribution, you may associate this one with a past episode of galaxy interaction or galaxy merger. So the holy grail, the ultimate goal of this quest would be to recover the star formation history of galaxies based on their observed cluster age distribution. By saying this, I'm already making one assumption. I'm assuming that all stars form in star clusters, or at least that there is a correlation of some kind between star formation as a whole and star cluster formation in particular. We will assume that this is the case. Next, we are facing two major tasks, two major problems. One is the incompleteness of the cluster sample. Not all the star clusters of a galaxy are detected. Some will be missed by the observations, either because they are too faint globally or because the surface brightness is too dim. And the second problem is that star clusters dissolve with time. We say that they evaporate. In other words, they give off their stars to the field. And those two issues, the incompleteness of the sample and the dissolution of star clusters, means that the observed cluster age distribution of a galaxy is a strongly encoded record of its star formation history. The dissolution of star clusters starts in the cradle already. Initially, a star cluster is gas embedded. It is a mixture of the stars which have already formed and of the gas which has not yet been converted into stars. So this is what is shown on this first panel of a sequence of L-body snapshots. Initially, a star cluster is gas embedded and it is very compact. Then, because of the stellar feedback of the newly born stars, you have some injection of kinetic energy into the residual star-forming gas, and as time goes by, that kinetic energy overcomes the binding energy of the gas. And as a result, the residual star-forming gas gets expelled from the cluster. The consequence is that all in a sudden, the stars of the cluster experience a gas-free, shallower gravitational potential, and they are now moving too fast for this new gas-free gravitational potential they sit in. As a result, the star cluster expands, releasing some unbound stars into the field. The end product, if the star cluster survives, which is not always the case, is a star cluster which has lost its gas, a fraction of its stars, and which has expanded. So this dynamical response of a star cluster to residual star-forming gas, to the expulsion of the residual star-forming gas, depends on many parameters. And I'm even not claiming that this list is a complete one. There is a star formation efficiency, which is the ratio between the stellar mass formed and the initial gas mass. We could also question whether gas expulsion is happening instantaneously or on a more adiabatic time scale. The star cluster could be in dynamical equilibrium to start with, or on the contrary be subvirial. There could be an external tidal field. More exactly, what matters here is the impact that the tidal field will have on the star cluster, and this is something that you measure via the volume density contrast between the cluster and the host galaxy. And you may also think about additional external perturbations such as GLCs or spiral arms. In this talk, I will focus on just the first parameter of the list, the star formation efficiency. And I will show you that in itself, this parameter is a very rough and very incomplete way of describing the problem. To know what is the gas mass fraction, which has been converted into stars, is not enough. We also need to know how the gas and stars of a nascent cluster are distributed with respect to each other at gas expulsion. So let me be a bit more specific. Let's consider a clump of molecular gas which is currently forming a star cluster. This panel shows you the star formation efficiency measured locally, so from one edge of the cluster forming clump to its center. It shows the local star formation efficiency as a function of the distance to the center of the molecular clump. You may consider a molecular clump achieving a global star formation efficiency of 15%. This is the pink line, and for which the global star formation efficiency also equates with the local star formation efficiency regardless of the distance to the clump center. This is on this assumption that the sequence of n-body models has built. So the idea is here that the cluster forming clump has turned the same fraction of its gas into stars regardless of the distance to the clump center. It is the same in the center of the clump and in the outskirts of the clump. Now we could consider another scenario where the global star formation efficiency is still the same, still 15%, but where star formation has been more efficient in the central regions of the protocluster and where it has been less efficient in the outskirts of the cluster forming clumps. So this is the radially varying star formation efficiency profile, and as we shall see, this helps improve star cluster survival. So let's have a look at the first scenario. This plot shows you the bound mass fraction versus the star formation efficiency. So the bound mass fraction is the stellar mass fraction retained by a cluster at the end of the response, of the dynamical response to gas expulsion. This is what I call F-bound. This is plotted as a function of the global star formation efficiency achieved by the cluster forming clump at the onset of gas expulsion. So global star formation efficiency means that the star formation efficiency has been measured average over the whole clump. So all these points correspond to n-body simulations which have been run mostly in the years 2000, often starting with a plummet density profile for the embedded cluster, and these are simulations which have assumed that the star formation efficiency is radially constant all through the cluster-forming clump from the center to the outskirts. When we assume that gas expulsion is instantaneous, meaning that it takes place in less than a crossing time, and that we can neglect the impact of the tidal field on the star cluster, all these simulations have achieved the same conclusions. You need the star formation efficiency of about 1/3 for the clusters to survive. If the star formation efficiency is less than 1/3, the bound fraction is 0, meaning that the star cluster is dissolved because of gas expulsion only. So basically, it tells you that this force panel is empty within 10 or 20 million years after gas expulsion. So, this is for this killing scenario. There is an alternative anyway, and this alternative is when there is a gradually varying star formation efficiency profile. Already in 2000, Fred Adams showed that if the star formation efficiency is locally higher in the clump center than in the clump outskirts, you can boost the survivability of the clusters. This is the result of semi-analytical calculations he did, and you can see that now if we have a global star formation efficiency of 15%, instead of killing the cluster is retaining a decent fraction of about 1/4 of its stars. What is remarkable about this paper is that it was published well before most of the N-body simulations which are described by that sequence of symbols. So obviously, the early survival likelihood of star clusters depends heavily on their initial conditions. And we need to know which initial conditions are the right one. So how can we distinguish between scenario A, the killer, and scenario B, the rescuer? So one possibility is to look at nearby molecular clouds in the disk of our galaxy. These are clouds which have a distance of typically a few hundredths parsec or 1 kiloparsec at most, and so they are so close by that they are young stars, meaning protostars and primate sequence stars, can be counted there. So on these maps of molecular clouds, each red dot corresponds to a young star, protostar, or primate sequence star, and the different tones of gray gives you an idea of the extension and therefore of the gas surface density. So a few years ago, Gutemus et al., following a survey of such nearby clouds, came with really interesting conclusions. They had a look at the star formation relation involving the surface density in YSOs, so young stellar objects, protostars or primate sequence stars, versus the surface density of the gas. Those surface densities are measured locally, so we are not talking about surface densities average over an entire cluster forming region or average over an entire molecular cloud. We are talking about surface densities which have been measured in the immediate vicinity of each young star. So in other words, in these diagrams and in this map, each dot corresponds to a young star with the corresponding surface density in YSOs and surface density in gas measured in the immediate vicinity of each young star. And the result that they got is that there is a quadratic star formation relation between the surface density in YSOs and the surface density of the gas. Now this is a really interesting result because you can rewrite this equation in the following way, saying that the surface density of the gas scales as the ratio between the surface density in y zones and the surface density of the gas. And this ratio being a ratio between a stellar mass quantity and a gas mass quantity is akin to a star formation efficiency. So what this quadratic star formation relation is telling us is that locally the star formation efficiency indeed depends on the gas density. This observational finding is matching extremely well the concept of star formation efficiency per free fall time, which was introduced by Krumholtz and Mackey. So the star formation efficiency per free fall time tells you what fraction of its gas mass an object is converting into stars every free fall time. So this is the definition of the free fall time. You can see that it scales as 1 over the square root of the gas volume density. So what this simple equation is telling you is that the higher the volume density of the gas, the shorter the free fall time, and the faster the pace of star formation. So keep in mind, denser implies faster. So the consequence is that for any given time span after the onset of star formation, say 1 million years, you expect molecular gas region with a higher density to achieve higher star formation efficiencies. So this is because, for instance, if this time span is about 1 million years, if the volume density is higher, the free fall time is shorter, and you will insert many more free fall times within your time span of 1 million years than if the free fall time is longer and therefore the gas volume density is lower. So this has consequences on the scale of cluster parent clamps, of cluster forming clamps, because we know that they have volume density gradients as shown on this map here. They are denser in their center than in their outskirts, and therefore we expect locally the star formation efficiency in the center to be higher than in the outskirts. So a few years ago I developed such a model in which I considered a centrally concentrated cluster forming clamps, and I applied to it a constant star formation efficiency per free fall time, and this panel is showing you the results in terms of the local star formation relation, so the surface density in y zones versus the surface density of the gas. So the panels on the right reminds you the observations that we have already described. These are the observed star formation relations obtained by Guterres and collaborators, this quadratic star formation relation. The green parallelogram is highlighting the bulk of the observations in the monocirrus R2 cloud, and the blue parallelogram is highlighting the bulk of the observations in the Ophiuchus molecular cloud. Those observed regions of the parameter space are highlighted with the same color coding in the plot on the bottom left, and the black dashed line corresponds to the average trend found by Guterres and collaborator for their complete sample of molecular clouds. And the red lines correspond to the model outputs at a time of 0.5 and 2 million years after the onset of star formation. Pay attention that the clump inner regions are located to the top right of the plot in the regions of high surface densities, both in gas and in stars. So to get the proper normalization between the model and the observations, I had to adjust the star formation efficiency per free fall time to a value of 10%, but where there is no fine-tuning of any kind, this is in the ability of the model to reproduce the quadratic relation of the observations. So these are two types of plots that you have seen so far. One is the quadratic star formation relation, and the other is the radial profile of the local star formation efficiency inside cluster forming clumps. So those two red lines, here the quadratic star formation relation, and here the evolution of the local star formation efficiency from low values in the clump outskirts up to higher values in the clump inner regions. Those two models, those two red lines, are two visualizations of the same physics, of the same models, telling you the same thing. Star formation is more efficient in the clump inner regions than in the clump outskirts. So as we have seen, that has consequences for the survivability of star clusters after the expulsion of their residual star-forming gas. This is the bound mass fraction, the plot of the bound mass fraction as a function of the global star formation efficiency, which I have shown previously. The symbols correspond to the n-body simulations which were carried out, assuming that the star formation efficiency is radially constant. And Shugel-Galiev has run new n-body simulations where he implemented a radially varying star formation efficiency, turning himself into a star cluster rescuer. For, as you can see now, the bound fraction is considerably improved. Now, instead of having a threshold for survivability of 1/3 in terms of the star formation efficiency, we have the threshold which is much lower, around 13–15%. And what is remarkable is that this is what we have achieved despite the fact that our simulations include the tidal field of the solar neighborhood, while in those simulations the tidal field is not included, or at least one can say that the impact of the tidal field is negligible. So far we have applied this denser is faster principle in a local way by comparing the inner and the outer regions of cluster-forming clumps. So in the outskirts, we have seen that star formation will be slow. After a given time span of 1 or 2 million years, the star formation efficiency in an outer layer will remain small, while in the inner regions, star formation is much faster, and after the same time span, we will have a much higher star formation efficiency. Now we can play the same game, and instead of comparing the inner regions to the outer layers of cluster-forming clumps, we can compare two different clumps which have different mean volume densities. So we can compare what's happening for a high-density clump and a low-density clump, and of course we can already anticipate that star formation will be faster in the high-density clump than in its low-density counterpart. So this is what is shown on this plot, showing the star formation rate evolution as a function of time after the onset of star formation. Here I have considered two different molecular clumps, one with a high mean volume density of 10⁵ solar masses per cubic parsec, and one with a much lower volume density, 3 orders of magnitude lower, 100 solar masses per cubic parsec. So I also give you the corresponding freefall times. In the first case, we are almost leaving the astronomical orders of magnitude we are used to. It's just 20,000 years, while in the second case, we have a freefall time of order 1 million years. So So on this plot, I have normalized the star formation rate to its initial value for the sake of an easy comparison. So one property of this model is that the star formation rate is decreasing with time. The reason being this is an equilibrium model, so there is no contraction as a function of time. So as star formation is progressing, the gas mass is decreasing, therefore the gas volume density is decreasing, and the free fall time gets longer. So everything is advancing at a slower and slower pace. So the star formation rate is decreasing, and you can see that this decrease is much sharper for the high gas density clump than for the low density clump. So one could say that for the low density clump you have a shallow slope, a slow evolution, while for the high density clump the slope is much steeper and the evolution is therefore much faster. The evolution of a star formation rate of a cluster forming region as a function of time is still very much debated. This is due to the fact that to estimate the ages of primate sequence stars is not a straightforward task. Nevertheless, in the literature based on age estimates of primate sequence stars or based on the counting of protostars and primate sequence stars, there are hints that indeed the star formation rate of cluster forming regions could be a decreasing function of time. So when you look at this plot, you can immediately realize that the stellar age breadth of a star cluster will be directly related to its volume density. So when the volume density is low, you will have a large stellar age breadth, meaning that the width of the stellar age distribution will be large, while if the initial gas density is high, we will have a very narrow stellar age breadth. So this is again an application of this denser is faster principle. So you expect for the low density clump C in blue a wider stellar age distribution than for the high density clump A. So what this is suggesting us is that the full width at half maximum of the stellar age distribution of a star cluster is a density indicator of its progenitor clump. So there are indeed hints for this in the literature. This plot is showing you the full width at half maximum observed for a sample of star-forming regions and young star clusters. So this is shown as a function of the mean volume density, and you can see that there are indeed indications that when the volume density is higher, the full width at half maximum of the stellar age distribution is shorter. So nevertheless, we would like to see more data in order to have more constraints on the models. So the takeaway messages at this stage is that if star formation proceeds with a constant star formation efficiency per free fall time, and I'm not pretending that things are happening that way in nature, so if star formation proceeds with a constant star formation efficiency per free fall time, the star formation efficiency will increase faster in dense gas. The consequences is that the local star formation relation is steeper than unity, so it will be called as superlinear, in our case quadratic star formation relation. Star clusters will survive better the expulsion of their residual star forming gas, and denser clumps will yield clusters with a narrower stellar age breadth than their low density counterparts. So this is again the quadratic star formation relation between the surface density in Y zones and the surface density of the gas. This is the observations that we started with. This slope of 2 has been confirmed by other teams of observers since then, especially by the team of Charlie Lada, Lombardi, and João Alves, where you will notice that they use here the counting of Y zones, so the number of Y zones per unit area. So some people use the mass count per surface area, some other people use the number count per surface area, and there are still some other people who use the surface density of the star formation rate as a function of the surface density of the gas. So this is not a problem since, as I have shown, we have obviously the time t included in our simulations, so we can use the star formation duration to convert the surface density in Y zones into a surface density of the star formation rate. The result is that the two lines of the model at age of 0.5 and 2 million years now merge together practically, except in the inner regions of the clump. Here you can see that we have, as expected, a drop in the surface density of the gas because gas has been converted into stars, and also a drop in the surface density of the star formation rate because, as I have explained previously, the star formation rate is decreasing as a function of time. In the low density regime, meaning in the outer layers of the clump, there is not much of evolution because the free fall time is so long there, several million years. So, what is interesting to note about the star formation relation is that you can define it if you have one single clump in your data set. So basically, let me remind you what we have done. We have considered one cluster-forming clump. We have considered it as a kind of onion, and for each shell, each layer of the onion, we have a measurement of the surface density of the star formation rate and the surface density of the gas. So this star formation relation is defined on a shell-by-shell basis, and therefore one clump is enough to define it. So this is the case for nearby cluster-forming clumps. Now imagine the following situation, that you move that clump from a distance of 500 parsec to a distance of 5 kiloparsec. At such a distance, you may not have the resolving power needed to count the Y zones inside the cluster-forming clump. So maybe that at that stage, at that distance, all you can plot in your star formation rate, surface density, and gas surface density, maybe that the only point you will be able to plot will be a mean value, a global value. So the mean surface density of the gas of the whole clump and the mean surface density of the star formation rate of the whole clump. And of course, one cannot define a star formation relation based on one single point. However, there is still a solution, is that you can still obtain a star formation relation if you can still define a star formation relation if you have a population of clumps rather than one single molecular clump. So let's have a look into that. So this is the definition of first order of magnitude, an estimate of the star formation rate of a cluster forming clump. So this is the very definition of the star formation efficiency per free fall time. The star formation efficiency per free fall time is the gas mass fraction which is converted into stars per free fall time. And if you divide both sides of the equation by the surface area of the clump, you obtain the same relation, but in terms of the surface densities of the gas and of the star formation rate. So now let's consider a population of clumps with all of them having the same, roughly, the same mean volume density and therefore about the same free fall time. So it means that you are left this time with a star formation relation with a slope of unity. So the surface density of the star formation rate is scaling directly with the surface density of the gas. This is what is shown by this blue line here. So instead of having the quadratic local star formation relation in red, we have a global star formation relation with a slope of unity. So shallower than the global relation is shallower than the local relation. This plot is showing you exactly the same kind of results, except that I have considered molecular clumps which are compact enough so that their mean volume density is 700 solar masses per cubic parcel. This is the mean volume density expected for molecular clumps mapped with in HCN 110. Now maybe that there is a caveat about this diagram, in the sense that if molecular clumps have such a high volume density, maybe it doesn't make that much sense to display the star formation relation at low surface densities, because we do not expect high volume density clumps to have a low surface density. So what I will do is I will move the global star formation relation in blue. I will move it to the right because I do not expect to have much data here in the low surface density regime. And this creates the impression of the breakpoint is what I call a composite star formation relation, because they have been obtained differently even if the underlying physics of star formation is the same. I have a quadratic star formation relation here in red for the local star formation relation, and I have a slope of unity here for the global star formation relation in blue. So, and because of this, and also combined to the lack of data here, I have the impression that there is a breakpoint in the star formation relation. And a breakpoint is exactly what Heidelberg and collaborators have found in their data for distant compact molecular clumps and nearby molecular clouds. So this plot is showing you again the surface density of the star formation rate as a function of the surface density of the molecular gas. The yellow points correspond to HCN molecular clumps. This is a global relation in the sense that we have seen that each data point corresponds to the mean values per HCN molecular clumps. In contrast, the green points correspond to observations in the solar neighborhood. In nearby molecular clouds, what they have done is they have discretized each molecular cloud in subsequent contours of the gas extinction and therefore of the gas surface density. And there they obtain a superlinear star formation relation. So in this superlinear star formation relation, each data point corresponds to one shell in one molecular cloud. So they interpret this breakpoint in their total star formation relation as a possibility for a surface density threshold for star formation. This is this sigma TH here that you can see at the basis of this thick gray line. So this suggests that there would be a surface density threshold for star formation at a gas surface density of about 100 solar masses per parsec squared, with star formation becoming increasingly inefficient as you go to lower gas surface densities. So the point I would like to make here is that this sigma TH, this breakpoint in the composite star formation relation, rather than a density threshold for star formation, that might be simply the breakpoint of a composite star formation relation with the transition between a global relation at high gas surface densities for distant compact molecular clumps and the low gas surface densities corresponding to nearby molecular clouds. So the takeaway message here is, I'm not claiming that there is or that there is not a density threshold for star formation. Whether it exists or not remains disputed. I would simply like to say that a composite star formation relation is not an appropriate tool to decide on the existence of a density threshold for star formation. So now we keep going with star formation relations and companies. So this is the most simple star formation relation you can think of. This is the relation between the volume density of the star formation rate and the volume density of the gas measured through a cluster forming clump. So you take a clump, it is centrally concentrated, the density is higher in the center than in the outskirts, and shell by shell you define the volume density of the star formation rate and the volume density of the gas. And you get a power of 1.5. The reason being simply that the free fall time scaling is 1 over the square root of the gas volume density. That gives you naturally a power of 1.5. Now this is the quadratic star formation relation in red that we have seen extensively all through this talk. And in fact, this quadratic star formation relation corresponds to exactly the same clump as the one which was shown by the blue curve. Simply, instead of showing the volume density of the star formation rate as a function of the volume density of the gas, I'm now showing the surface density of the star formation rate versus the surface density of the gas. And as we have seen in this case, the slope is 2, about 2. And finally, another star formation relation that we have encountered, this is the global star formation relation, when you consider only mean values of the volume density of the gas and of the volume density of the star formation rate. So this is when you consider that the mean volume density of molecular clumps is constant, the free fall time is constant from one clump to another one, and so you are left with a linear star formation relation between the surface density of the star formation rate and the mean surface density of the gas of the molecular clump. So we have 3 different types of slope, 1.5, 2, and 1. So this is a summary, depending on whether you go for local measurements, whether you work in the volume density or the surface density, and this is in the case of a global measurement, so a clump by clump measurement, you have a slope of 1. So regardless of what you want, I have something for you, whether you want a slope of unity, a quadratic slope, or maybe you are picky and you want something in between. I also have something for you. So the points I want to make here is that the fact that the star formation with a constant star formation efficiency per free fall time doesn't mean that the slope is necessarily 1.5, because this is an argument that I have sometimes seen in the literature. Star formation with a constant star formation efficiency per free fall time, the slope is not necessarily 1.5. You can get a slope of 2, as I have just seen. Conversely, a slope which is not 1.5 1.5 does not imply that star formation does not proceed with a constant star formation efficiency per free-fall time. In all these models, in all these slopes that I have shown you, the physics of star formation is always the same. These are models which always assume a given star formation efficiency per free-fall time of 3%. The physics, the modeling is always the same. It's simply what you measure and how you measure it which brings you those different slopes. So the point I want to make very strongly here, that the diversity of slopes depends as much on what is measured and how you measure it as much as on the physics of star formation. So do you work locally, globally? Do you measure the surface density, the volume density, maybe the total mass? This will influence the slope of the star formation relation as well. So I will leave you with my conclusions. You will remember that we started the talk with the idea that the age distribution of star clusters could be built on to recover the star formation history of their host galaxy. So such an age distribution is corresponds to a spatial scale of many kiloparsecs, sometimes several tenths of kiloparsec. And as I hope I have convinced you, you will understand that to convert this observed cluster age distribution into the star formation history of galaxies, we need to understand what's going on in the parsec scale, on the scale of cluster forming regions, and that brought us to the star formation relations of molecular clouds in the solar neighborhood. So I will simply conclude by saying that all these special scales and topics are tightly related: the star formation relations and their proper interpretation, the stellar age spreads in clusters, the survivability of clusters after gas expulsion, and building on the cluster age distribution as a tracer of galaxy star formation history. Thank you.